everyone, and welcome to today's STERIS Tech Talk on activation testing and X-ray processing. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is Ashley Maru, and I'm the Associate Product Manager for STERIS Applied Sterilization Technologies. I'll be the host for today's event. Our presenter today is Deepak Patil. Deepak is the Senior Director of Radiation Technology at STERIS AST. Deepak joined STERIS in 2000 as a dosimetry analyst with the Dosimetry Services Group. He has subsequently held positions of increasing responsibility throughout his 20-plus years and led the transition from an internally focused gamma dosimetry support team to a customer-focused radiation technology neutral organization. Over the past several years, Deepak has assumed the leadership role for our radiation physics team, our Radiation Technology Center, RTC, our radiation tech team, and most recently, the Libertyville Laboratory. Deepak is a recognized industry leader serving as an executive committee member on the ASTM E-61 Radiation Processing Committee. He is also a member of AMI and KERMS. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS Applied Sterilization Technologies YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Deepak to begin the presentation.
Thank you, Ashley. As Ashley mentioned, I'm Deepak Patil, Senior Director of Radiation Technology. Today we're going to be talking about activation testing and X-ray processing. So we have multiple sessions. My counterpart in Europe, Hervé Michel, had given a webinar this morning on the same topic. So today we're going to be talking about why we assess activation, activation principle, assessment of activation, the methodology that we use to do this assessment. We'll look at a couple of case studies as well. So why do we assess activation? Well, artificial radioactivity occurs when human operations result in radioactivity being created. Sometimes, this is known in the nuclear reactor world, for example, as a nuclear fission product, which results from bombardment by photons or particles. Sometimes you might hear the term induced radioactivity, same thing as activation. And assessment of induced radioactivity or activation in healthcare products that are sterilized with radiation helps us determine whether or not activity exists higher than a background level. And we'll talk a little bit about that more later. In terms of medical device manufacture and sterilization, we must consider activation or induced radioactivity for anyone that may come in contact with the product. That's including our teams that irradiate the products and handle the materials, all the way through the transit, the hospital, the patients, obviously. So anyone along the way that might come in contact with that device. So the reason, the standard in 11137 Part 1 does require an assessment for induced radioactivity for electrons that exceed 10 MeV or X-rays that exceed 5 MeV. So our X-ray irradiators will run around 7.5 MeV, really to improve the efficiency. That's the highest rate of conversion from electrons to photons or X-rays. It's about a 12 to 15% conversion rate. So why do we, kind of adding to that, why we go over 5 MeV or why we're running at 7 MeV, this plot shows you penetration characteristics of different radiation modalities or sources. You can see in yellow we have E-beam at 10 MeV, which electrons do not have a lot of penetration capability, so you can see the depth is fairly shallow for that. Cobalt-60 provides more depth, but because X-rays, as you can see on the right here, X-rays hit the product, and we'll see another chart on this a little bit later, but they hit the product directly in a singular direction coming out of the scan horn. whereas cobalt-60 is what we call isotropic, which means that the photons are shooting all over the place. And again, we'll see a graphic of that a little bit later. But as you can see here, between 5 and 7 MeV, at 7 MeV, we have a better penetration than we do at 5. And we want to try to maximize that penetration, which is why we'd run our energies around 7 MeV. So I talked to on the last slide about isotropic. So this is what we're talking about here. Basically, this is a cobalt-60 source rack, and the arrows are the photons, which are shooting all over the place. They're not in a singular direction. So for those of you familiar with the cobalt-60 irradiator, you'll know that the source rack comes up, and basically we try to surround the source rack with the radiation containers to maximize these different photons that are shooting out into absorbing into our products. On the right here, you see, as I mentioned earlier, this is X-ray. Basically, the red is electrons. It hits the converter plate, which is usually tantalum, and in green represents the photons. But you can see the direction is much more singular than it is in the photon form cobalt-60. On the top here, we have decay scheme of cobalt-60, which has a known average energy of 1.25 MeV. So the thing with X-rays is that the energy will not exceed the incident energy or the energy of the electrons. So if we run a 7.5 MeV for X-ray, that's the highest energy we'll get. But you can see the energy spectrum is kind of all over the place. So there's not a singular energy like there is in cobalt-60. So the principle of activation, let's talk about that a little bit. When a photon strikes a nucleus, basically a particle is ejected, or can be ejected, I should say, from the nucleus, if its binding energy is less than the absorbed photon energy. And then what happens is the remaining nucleus may be radioactive at that point because it's now an unstable element. And the major reaction that can lead to these photon-induced activities are basically 5 different items here we'll look at real quick. There's the photon-neutron reaction, which really is expulsion of a neutron. And then the rest are really photon, deuterium, photon tritium, and photon alpha. And you can see here, it's just the hydrogen atoms is adding deuterium and then tritium here. And so the last one is an absorption of a photon alpha, which is a helium 4 atom. So what happens is, looking at that graphically, basically, in a 7.5 MeV irradiator, the energy of the energy of the photons can generate lower neutron radiation during the interaction with matter. And so we can see that here, that the photon hits the element and then it expels a neutron in this example, and now this is unstable, which makes it radioactive. For a photon-neutron reaction to occur, we mentioned earlier, the photon must strike the nucleus with energy that's more than the binding energy of the atom. And we'll see a little bit more about that in a chart later. So neutron capture, what is neutron capture? Basically, a small number of neutrons can be generated in the X-ray target. So when the electrons hit the target, and basically those are deuterium, carbon-13, oxygen-17. They're very small, as you can see, that close to the natural abundance as well that already occurs in nature. So the capture of these neutrons basically results in activation. It's a second order effect, and we can see that graphically on the bottom here with the picture. And many times what happens is, even though it's over the background level, and we'll look at a case study later to understand this more, the measurable amount of activity is very, very low. And so when we talk about activity or induced radioactivity, we're really talking about 2 things. One is that the initial step is the activity in the equipment you're using to count higher than the background level. And if it is, then the second piece of that, it doesn't necessarily mean it's radioactive, because there's a second part of that, which is it over the exempt quantity to be considered radioactive? And we'll look a little bit more on that later. So activation reactions occur. They produce a new isotope of a new element if a proton was emitted, or the original element if a neutron was emitted. So each isotope, as we mentioned, has a threshold energy for these reactions. and there's a neutron cross section that every element has a cross section that basically determines the probability of interaction with any material coming in. So the last thing to talk about here is that if a daughter product of the reaction is stable or the threshold energy is above 7.5 MeV, there's really no concern for activation of that isotope by the primary X-ray. So this is we published a paper in the AMI, one of the AMI newsletters several months ago, and this is one of the flow charts we have in terms of, I'll go through this quickly, in terms of how to, the decision-making process and whether or not to test something for activation. So obviously you want to start, are the X-rays greater than 5 MeV? If the answer is no, then there's no concern for induced radioactivity. If there's yes, the energy is greater than 5, then we want to ask, or we want to understand, are there any metal components? If the answer is no, one of the things we've really discovered is there's a lot of materials that have metallic elements in them that aren't necessarily metals. Saline solution is one that has sodium. So, there's other things that can activate. So you want to ask the question, are there metals in those different materials that you wouldn't traditionally think have metallic elements in them? There should be a no box down here that would lead back here if the answer is no. So if there are metals in there, we use a trigger of 2 hours really to look at whether or not will that activation remain for more than 2 hours, and that really is a result of how long it would take for us to irradiate something and then get it through our process and shipping. So it's activated with less than 2 hours, then we don't really have a concern. It'll die off before it would ever be used, obviously. And if the answer is yes, it would be more than 2 hours, then we want to ask, are there any elements likely to cause activation above the limits? I talked earlier about we've got are we above the background count? And we're kind of at that point here. If the answer is yes, then is the level of activity higher than what would be considered radioactive, which is there's a lot of published documents, and a lot of this has to do by country. And so in the US, for example, they call that exempt quantities. Is it greater than the exempt quantity for that isotope? If it's not, then it's not considered radioactive, and it can be treated just like any other product. And we do that through an evaluation. We have a process to evaluate that through different calculations and literature references. And so if we go back to here, and if we end up that there is a probability that the activation is above that exempt quantity, so in other words, the product is considered radioactive, then we got to do another assessment, an empirical assessment, to determine if it's above the limits. And at that point, we engage with the customer to understand what the options are going forward. And if there's no probability that the activation is above the limits, then we just go back to this. As I mentioned, that product then becomes just like any other product that is not considered radioactive. So this chart talks about, looks at risk of activation for principal elements used for medical devices. So really, if we look at, there's in the comments row here, in the comments column, you'll see a 1, 2, 3, or 4. And at the bottom, you can see really for 1 and 2, we don't have a concern because the daughter products are stable, or it's only deuterium that's present. For 3 and 4, there could be a concern for some of these elements. I will tell you, of all the stuff that we have tested, of all the products we have tested, both on and we'll look at this a little bit, but Danik in Switzerland is our X-ray RTC site in Europe, and they perform this testing through a second-party lab. And in the US, we do this testing in Libertyville, Illinois, at our RTC site, Radiation Technology Center. And so we have had some products that have been above the background level, but nothing has been above the exempt quantity on both the Europe side and the US side for any products we've tested. So it's all either died off quickly, or the count level is well below something that would be considered radioactive. So I want to talk a little bit about the ways we do this assessment. I talked about Daniken and Libertyville, so we'll look at that a little bit more. So there's really two options here. You can perform a screening measurement, of the product to determine whether it's above the background count level, basically. Or you can perform a qualitative and quantitative analysis, which is much more involved, and it will identify the different isotopes as well. In the US, we do option 1, which has worked fine, and in Daniken, they do option 2. They send it to a lab with a germanium detector, which we'll talk about in a little bit. One thing to mention is the activation of the elements is directly proportional to the dose, which means if you receive more dose, the activity of anything that is above the background count level would be proportional to that. So double the activity just says double the dose. So this is a screening process. We use this in Libertyville. Essentially, we have a Ludlam 54A, and we have done a lot of work to qualify that, that equipment and to determine the appropriate background level. So we do a 10-minute count, basically. So what happens is when we receive products for X-ray max dose testing, we ask for additional samples at some amount higher than the maximum dose. As an example, if a customer sends us a 40 kilogram product, we will irradiate to 40, obviously, for their max dose testing, but then we also ask for 44, for example, so we can test for activity at a higher level than the max dose. So we irradiate in X-ray to 44 kilogram in that example. It goes into the detector and does a 10-minute count. We do a background count prior to putting the sample in the chamber, and we also measure a check source. That's number 3 is a background count, and 4 is the check source, so it's a known activity, just to make sure that it's counting accurately. And then we count the product. Initially, our employees, our team, will use a handheld meter to make sure that it's below the activity level that they can handle it. And we haven't had anything that has been over that level when we've done the probe assessment. So it then goes into the chamber and does a 10-minute count. And you know, we have our count level of what's considered above background. It's called the critical level. So anything above the critical level is considered activated. And at that point, we do an assessment, as I showed in the flow chart, an empirical assessment to determine whether or not that level, that count level, is greater than what we would consider the exempt quantity. The second method I talked about is the approach that they use in Daniken, which really is similar to what we do in Libertyville. We need to expose the samples to a higher dose than the maximum dose of the device. After that, they send the samples to an approved laboratory with the germanium detector. The laboratory performs a measurement, and if it is activated, the lab will define the radionuclide, both its level of its count level and also which radionuclide is present. So this is just a result of some actual products that were tested here. You can see the doses that were received and the element that was activated. And so I'll show a little bit to give some context on the level of activity versus the exempt quantity level on the next slide. And these are the different radionuclides that were present and activated, and then this is what was measured as far as activity. So a couple things I wanted to point out here. This chart shows actual elements, for example, sodium, the radionuclide, the measured level they had. But then you can see here in this column, this is a maximum acceptable level. And you can see here, we're well below all those levels. Even copper, which had the highest activity, is well below what would be considered radioactive for copper. And a lot of these cases, these half-lives are on the order of hours. They decay fairly quickly, but we have not had anything close to coming to the exempt level or maximum acceptable activity. As a point of reference, you know, you can see here, these are the counts we had, or the activity levels, sorry, in becquerels. The human body has about naturally occurring about 8,000 becquerels, and you know, we're well, you know, even these quantities are well below anything that's in the human body. So we haven't had a concern as far as activation of products so far. This is just a pie chart to show the different elements that have been activated. You can see sodium by far is the most. Probably mostly has to do with the sodium's occurring in a lot of the products that we have tested. And then these are the different other elements that we've seen, but it just gives you a little breakdown of what the different elements that have been activated. But again, I want to stress that activated means above the critical level well below what would be considered radioactive. Finally, I just wanted to, there's some publications that are out there. I know this, activation is a kind of an unknown area for a lot of people. So there's more and more publications coming out. As Ashley mentioned, this presentation will be on our YouTube channel. So all these references will be available. I'm sorry, you'll be able to see the references on the through the presentation if you wanted to find more information on it. So just to kind of tie things together and conclude, so we do an assessment of induced radioactivity, which is required by ISO 11137 Part 1. And there's a couple of different approaches you can take to do that we talked about. And we need to consider the risk for the persons that are handling the product in terms of radioactivity, which can be based on comparison to exempt levels. While a lot of the assessment can be based on theoretical calculations, we can eliminate many materials from consideration due to low probability of induced radioactivity occurring. One thing we're doing is building a library of products that we've tested. So that will give us information to do an assessment to say, we've done sodium in these quantities and it doesn't make it radioactive in terms of over the exempt level. So there's an opportunity there for us to potentially reduce the number of tests we do by creating that history and library as we go forward. And that's it.
Thanks again for joining us today. This concludes the webinar.